So to this point, essentially what we've done is we've had these sort of, well, we've done two sort of big things. The first thing we've done is we said that there's this idea of if we record certain data, it tends to, you know, if we were to say plot data in a certain way, we often recognize that there's some pattern. And so what we do is we say that certain things are normally distributed. And then we ask certain questions about that. And, you know, we're kind of glaring over the details, but the point is that for many different scenarios, when we record data, we often recognize a certain shape to this data, sort of like the bell curve. And so we ask, you know, how accurate does data in real life represent, or can it be represented or modeled or explained by this curve? So once we said there's this curve out there, then we said the important thing about this curve is the area underneath it. And if we understand how to calculate that area using tables or using calculators, then we can answer certain questions that, you know, we might call toy problems, little textbook problems about probabilities. So that's really what we've been doing to this point. And we're going to get into a little more of the details shortly of why this stuff is useful and accurate, not just doing problems in a class. But before we do that, I do want to point out that I don't know if you saw this yet. I made this little calculator if you want to use it. And I posted it to GeoGebra, or excuse me, to Canvas. So I'll show you how to use it if you haven't figured it out yet. So what I'm going to do is I'm going to share this screen. So if you log into the Canvas, the first thing you'll see is I have the lectures embedded now for those of you who want to watch them. And if you go down on the syllabus page, you'll see, I don't know, where did I put it? Where did it go? Maybe I didn't post it yet. Did I put it in an announcement? Oh yeah, I put it in an announcement, I guess. No. Am I losing my mind? I guess I am. Jeez, oh man, oh Grady. Well, then I lied to you. I swear I posted this on. Well, we'll get it for you right now. So anyhow, I'll post this link to Canvas for you, but basically what you have here is I created a table to help you calculate these probabilities that we've been doing the last few classes. So once you have what we call your z-value or your z-score, and you wanted to calculate, so for example, I might want to know the probability if I go back to the whiteboard, I might want to know the probability that, say, Z is less than 6.67. We actually computed this for a problem 2 classes ago. So if I want to compute this probability, there's a few ways I can do it. I can go on the internet, find a calculator. I can look it up in the back of the book. So what I decided to do is I wrote this little applet if you want to use it. And so all you have to do is put your number here, 0.67, hit enter, and you'll see that a couple things happen. First off, you'll see that there's this area under this red region. That red region is the actual area under the curve up to 0.67. And that number, that area of that red region is the probability that you're looking for. It's this number right here, 0.74857. So if you round that off, let's say 0.7486 if we want. So again, it's pretty straightforward how to use this thing. If you want to use it, I'm not saying you have to, but it's there for you. You plug in your values. Notice, for example, if I plug in 0, if I want to know the area up to 0, you'll see that it's 1/2 as we expect. If I want to know the area up to 2, it gives me 0.977. So if you have any questions about this thing, just shoot me an email or whatever, or ask now. But anyhow, I think it's pretty easy to use, and it's quicker than going in the back of your book. Because we're going to continue to use these things, and you kind of want to get efficient at calculating. Any questions? Okay, no questions? Good. Means you're all sleeping still.
You want us to say something then?
Okay, so a couple questions that you might have and how we can answer them. So a couple remarks or questions. So first off, if you think about all the problems that we've done the last class or two, our last topics where we're saying determine this probability, determine that probability. If you look at how I worded all those questions, I said, assuming something is normally distributed, assume this is normal distribution, assume. We're doing a lot of assuming. And that's because we actually want to be realistic. I don't want to pretend for a second that every single thing that we study in this world is going to be distributed normally. And we have to be careful with that. So we might ask ourselves, how do we know something is normally distributed? So an example of what I mean by that is if you went and took 100 adults and calculated their blood pressure, and then you went and laid that data out on a chart or a graph, you might say, okay, it looks like it's normally distributed. Why would you say that? Well, you might say that because, hey, when I plot it, it looks like I get this little bell curve. But then you would have other questions. Okay, if it is normally distributed, what's the mean? And then if you found the mean, you might say, okay, what's the standard deviation? Now, you guys know how to calculate that. We talked about how to calculate those numbers a while back. And even if you have a large group of people that you're sampling, like you're going to sample 100 or 1,000, a calculator can easily compute those things. But one of the caveats we want to do to get you to think about, and if you remember way back on like the first or second assignment, we talked about this and we did some stuff in class. If I go and select 100 adults and look at their blood pressures, it very well may be that my data depends on where I select these adults, what time of day I do this sort of gather this data, where do they live in the world, what kind of economic, social background. I mean, these things all might affect the 100 people that I choose. And then another thing to concern yourself with is how many people is enough to get a good reading. If I just went and took 5 adults and calculated their blood pressure, do I really get anything meaningful from that? Does 100 people give me meaningful data? Well, 1,000 people, well, 10,000. So when we start thinking about questions like that, we have to start thinking a little more carefully. So these are the kind of questions we want to keep in our mind. How do we know something is normally distributed? How many sort of values, wow, I can't spell today. So Tuesday mornings. So well, let's not say how many. That seems to be a very baby way of saying it. How about this? What size of my sample, or what size should my sample to be? It's a better way of saying it. So I'll give you an example of what I mean by this in a second. So this is what I was saying a few seconds ago. What size should a sample be to be sure it's good? So again, if I go back to the blood pressure example, if I just ask 100 adults if I can compute record their blood pressure, is that going to give me reliable data? What if I said 1,000 or 10,000? How do I know how many is enough to get reliable data? And so if you ponder that, you might start to remember a few things we talked about early in the semester when we were showing you how to calculate means and standard deviations a few months back. We had these sort of adjectives in front of the word mean and standard deviation. You might remember them. They were sample mean and population mean. So let's bring that back in. So you might say to myself, you might not remember what that means, but let's take our time machines in our brain. Let's go back a few months. We were calculating means and standard deviations. We were doing it on Excel. We were doing it by hand, and I even showed you. Let's go to it right now. Go back to the internet. We use this website called Wolfram Alpha, which I'll show you this again. So hopefully you guys see Google right now. So if I go to Wolfram, oh, it's not showing anything. Sorry. So if I just ask it to compute the mean of some numbers, it gives me this mean. And what if I said standard deviation? So what happens here, and you guys will recognize this hopefully from what we went through a few months ago, I gave it a few numbers. I asked it to compute standard deviation. And you'll notice that Wolfram gives me a disclaimer. Why does it give me a disclaimer? Well, what we found out when we were using the built-in standard deviation on Excel a few months back is that when we were getting our answers, it wasn't agreeing with other software answers. And so if you remember, we asked ourselves, are we doing something wrong? And then we came to Wolfram and we realized that Wolfram is giving us two options. It says there's this thing called a sample standard deviation, and then there's this thing called population standard deviation. And so we went into a big spiel about how there's two different ways of thinking about this, and we asked you to go read about it. So I think I even typed something in the web browser in class like, what is the difference between population and sample, variance, standard deviation, whatever you want mean? And so I asked you to read about this and think about it. And I also put questions, I posed them to you sort of like I'm doing now. So again, this is something I think would be beneficial for you to read and think about. And you can, there's lots and lots of answers on the internet. But a good way to think about this is as follows. If I said we want to know the average, if we'd like to know the average blood pressure of an adult, I think you would all agree with me that it is humanly impossible for me to record every single living adult's blood pressure. It would be impossible from a practicality standpoint. How could I do that? Since we recognize that it's impossible, the next thing we do is we say to ourselves, okay, well, how many do I really need to record to get reliable information? I think our intuition tells us if we just check 10 adults, we might not get reliable information. However, if we did 10,000 adults, we might get reliable information. Does anybody have a question about that or a comment? Does anybody have sort of a question or a comment? One way I would encourage you to think about this is you can think about the population as sort of the theoretical value. So here's a good way to think about it. Go back to our blood pressure. We would like to know how blood pressures of adults are distributed. So we might say, okay, we can't go and record everybody because we just can't. So let's just pick a number. Let's do 10,000 adults. We would call that a sample of the population. And suppose we said, okay, I'm going to do 10,000, you're going to do 10,000, someone else is going to do 10,000, someone else is going to do 10,000. And then we say to ourselves, okay, if we start doing it that way, what can we make of the statistics? Because every one of us who does, suppose there's 30 of us in this class. Suppose I said you have to go out and calculate the blood pressure of, say, 1,000 adults. Well, if I go and do that, I'm going to get a mean. Then Liam, you're going to get a mean. And then everybody else is going to get a mean. So we're going to have 30 means for our samples. And the question is, how do we analyze those means? How do we make sense of it? And so that's kind of what we want to study now. Or not necessarily study, but think about. Does anybody have a question? Comment? So two legends studied these things. So the first was de Moivre, and the second guy was this guy named Laplace. So the three questions I posed and even more were interesting. And by the way, they did this back in like the 1700s, 1700s, which is quite a while ago. And it always is amazing to me that this kind of stuff was studied long before technology of computing. They must have spent a hell of a lot of time crunching numbers instead of thinking critically. But nonetheless, they were able to do it. And one of the big ideas that came from this is what's called the central limit theorem. By the way, you should Google de Moivre and Laplace. They did lots of good stuff. So the big result is called the central limit theorem. So again, keep this in mind. Here's the issue. Very first day of class, I said, what is statistics? And we talked about the statistics. This is this sort of the collection and the analysis of data. It's a very generic way to describe what statistics is. And then we gave you some problems for homework and asked you to analyze some statistics. And many of you didn't really know what that meant. And that was for good reason, because we didn't have any tools for analyzing. And so we told you a big part of analyzing this is this idea of probability. Probability sort of goes hand in hand with this idea of data if we really want to analyze it and get good, useful information. And so we want to have examples in the back of our head. Or I had a teacher that always used to say, keep examples in your back pocket. So you want to realize what our goal is here. And so the sort of the story I'm going with right now is this idea of what is the blood pressure of an adult. But I could use anything. I could use what is the height of an adult, or you could think of anything you might want to study or analyze. Yesterday, oil prices were in the news. You want to analyze oil prices? Go ahead. You want to analyze unemployment. You want to analyze average salaries. You can imagine what you might want to analyze. But in any of those scenarios, the big questions still arise. How many do I need in my sample to get reliable data? If I think that this data is distributed a certain way, perhaps normally, how do I know that? And then not only that, the next thing would be, how confident am I that my data has a certain feature to it? So that's the first time we've heard that word, and we're going to hear more of that soon enough. How confident are we? How confident are we that our sample size is reliable? All right, so this all seems overwhelming. So the best way to do it is to do an example. This is fun. Let's get another color. Wonder if everybody's alive. How many are on here right now? 7. That is so cute. It's like whenever you get married, they say that whenever you invite how many you invite, this is a good statistic right here. I wonder how accurate it is. But whenever you get married, they say expect 30% of the people invited not to show up. And that's about where, we're the opposite of that right now. We're like 30% of the class shows up for lecture. 70% stays home, sleeps, whatever they're doing. I don't know. Okay. So let's motivate with some sort of example. Uh-oh, someone's chatting up. I don't know what that even means, Liam. From my theory, I don't have a theory.
About like the marriage thing and people showing up here.
Wait, the what thing?
Never mind.
Oh, I thought you were serious. Man, see, Liam, this is why we need to be back in a class, because it was more fun when I could ask you random questions based off of what crazy ass shirt you had on or something. This whole this quarantine nonsense.
Yeah.
It's not as enjoyable as sitting in a classroom with you guys. Plus,
I'm not putting miles on my car, so I'm happy.
What's that?
I said I'm not putting miles on my car, so I'm happy.
That's true. There are some side benefits to this. and I don't even like this because I have two monitors and I feel like I'm not even looking at you guys because I'm writing on this pad and I'm looking at one screen. So it always looks like I'm not paying attention to you guys. I feel like I'm doing a terrible job, like I should be fired. But then again, I've seen some of the other instructors out there. I would love to know what they're doing right now. If anything, they might just be telling students to read. I have no idea. Okay, so let's sort of give an example that illustrates some of these concerns and questions that we had before. So this is a topic in my house right now, by the way. So here we go. So a recent study suggests the following. So a study says we have children between 2 and 5. Watch on average 25 hours of TV a week. Now, when I say TV, that can mean anything. Media, Netflix, whatever. Their Kindles. So here's the question. If we select 20 children in this age group, let's determine the probability that their average TV time is more than 26.3 hours. So let's read this very carefully. So we have some research out there. We don't know how accurate it is. Some company is telling us that they did a research study and that on average, the mean, so if you take all the children on the planet between 2 and 5, the average amount of time they watch television a week is 25 hours. And if we want to, well, I guess I should learn how to spell Gindrin. This is incredible. So what we would like to know is, suppose we take 20 children at random and compute their average TV time per week. How likely is it that it's more than 26.3 hours? Okay, so does anybody have any questions about what we're doing here? Okay, so if we let's put a little green or red. So this question looks very much like the questions we did on the last homework and that we talked about last week. But you notice, first off, I didn't say anything yet about the normal distribution. Okay, so what if we assume that the data the study gave us is distributed normally? So, because as of right now, there's not much we can do. I mean, how are we going to determine a probability unless we have an idea of how it might be distributed? So let's suppose that we assume this data is normally distributed. So for let's assume so what would we need? We would need a sigma. So let's say the standard deviation is 3. Okay, so again, I'm over here pretending like some of you are actually thinking about this. You're probably not. You're probably like sleeping. Or like, are you going to finish the problem? Okay, so cover my computer here. So the question then becomes, well, I shouldn't say the question becomes, I said, how would we answer this? And if we assume there's a normal distribution with some variance, I mean, again, if we collect data, we can easily compute the mean and the standard deviation and the variance. So, you know, we can, it's okay to assume that it's out there. So the question is then becomes, do we just repeat what we did last week? Do we just say, okay, we have some random variable, which is the average time children watch. And do we convert, you know, what I mean is, do we do this? I mean, we could use it, I guess, but is it good information? So these are questions I'd like you to think about. So oftentimes, the best way to gain any sort of feeling for what's happening is to actually do some problems. Another thing would be carefully read this problem and what it's asking and compare it to the previous problems that we did. So if you look at the wording of this problem versus the other examples, you'll notice that there's one subtlety. So if I go back, in the problem I said, determine the probability that their average TV time. So in this particular question, what makes it different than the ones we've done in the past is I am asking a question about the mean of a sample. So there's a subtlety here. If you carefully read this, you'll say the question is different in the sense that I am curious about the mean of 20 people. So that is the mean of a sample of a larger population. So note, the question is about the mean. Oh no. If you go look at homework 8, you'll notice these problems, I'm not asking you about the means. In all those problems, I'm asking you something different. For example, I gave you a problem about new homes. What is the cost of a new home? And I said that the average cost, according to a study, is blah. It has a standard deviation of blah. And then I would say something like, determine the probability that a new home will cost less than something. That had nothing to do about me asking about the means of a sample. Then I gave you something about commuting times. Or I gave you something about credit card debt. In those questions, I was asking about a specific random person or random, what's if I randomly choose a college student, what's the probability their credit card debt is blah. If I choose a random commuter, what is the probability their commuting time is less than blah? So there's a subtlety in how these problems are worded. Here I'm asking a slightly different question. I have a random variable of means is essentially what I'm doing. Does anybody have a question or a comment? Comments? So I hope that you will take some time to sort of read these things carefully. Because this question is asking us, in some way actually, to compare the means of 20 people. Are we going to get information about, because we could look at this idea from one perspective. We could say, if we take 20 random people and look at their average time, how do we get any reliable information given the fact that we have some study out there? Okay, so that's sort of what I want you to think about, not just right now, because obviously some of you won't even be watching this right now. But if this is something you want to learn, these are the kinds of the deeper ideas that you need to ponder. The next thing to think about is, what if you said, okay, I'll do 20 here, and then I'll do 20 tomorrow, and then 20 the next day, and then 20 the next day. Or maybe you call up some research group that says they're going to do 20 people. They're going to do 20 different random selections of 20 people 10 times a day. And now you start really getting all types of averages you can compute. I have a mean here. I have a mean there. I have 20 means I computed right now. Then later today, I'm going to have 20 more. And then someone else is going to have 20 more. And what we're going to try to think about is what happens, what will happen to those means. Will we see a pattern? So if we go back to what we talked about earlier, we talked about the idea of sample versus population means and standard deviation. And so since the problem is asking us to look at a sample of a larger group, we're not looking at all children between 2 and 5. We're selecting a sample of that. We're selecting 20. So again, let me make this clear. We're choosing a sample of 20 children from all children. So since we're choosing a sample of 20, we might try to use the sample standard deviation. So again, let me reemphasize this. We're not looking for an individual value. We're looking for a value of a sample. In particular, the mean of a sample. So what does this mean? This means that we use the formula z equals, and if you go way back, we use this thing x bar. We put a bar above it because that's the sample mean. And we had this particular formula. So there's some thinking about with this formula. I now have this bar above the x, because remember, we're talking about means. So what is x bar? That's the sample mean. Remember, in this particular problem, what we're interested in is we're interested in knowing the mean of the sample. And I keep repeating myself and reiterating it, but it's very important to distinguish the difference we're doing now compared to what we did last week. So this formula looks very similar to what we used, only there's a bar above the x. And now instead of just dividing by sigma, we're dividing by sigma over the square root of the sample size. Does anybody have a question or a comment? So what I would encourage you to do is think about why we have a sigma over the square root of n. More particularly, you might want to think about, and this is where learning happens, why sigma over the square root of n instead of just sigma. So what do I mean instead of? Well, if you go to our formula when we were doing single values was z equals x minus mu over sigma. Now we replaced x with x bar, and we replaced sigma with sigma over root n. What would sigma over root n be measuring? Why is there a square root there? What does this have to do with sample standard deviation? Ask yourself, what was the difference between the standard and population formulas? If you remember, one had the square root blah, blah, blah over n. The other had the square root blah, blah, blah divided by n minus 1. Does anybody have a question, comment? So another thing I'd like to point to your attention is I stated a problem, and I know most of you are just like, well, what's the answer? What's the answer? That's not the point of this exercise right now. The point of this exercise is that hopefully you're thinking about the fact that A, I'm going slow. I'm pausing. I'm giving you moments to try to have a learning experience. Maybe not right now, but maybe you watch this later. I'm giving you ample time to go back and compare the problem I stated briefly here and compare it with the problems we did last week. Even though it looks almost an identical type of problem, it's asking a completely different question. And then not only that, how does this question that I'm asking, how is it related to what I started babbling about at the beginning of class, the bigger picture? Now, you've heard me use a phrase a couple times, sampling the means, a sample of means. That is a theme that's going to pop up. We are asking a question about a sample size. In particular, we're asking a question about the mean of a sample of 20 individuals. And so at this point, what I'm asking you to do is I'm asking you to think about why the formula must change and why is it what it is. Why this sigma over root n? Why not just sigma? Does anybody have a question? Now, do not get discouraged because I'm asking you a deep question here. So what I'd like you to do is I'd like you to think about this. Notice how I phrased, especially this last slide. I said we might want to try using a sample standard deviation. Now, if you pay any attention, you know, maybe this is misleading actually. I should rewrite this. So now that I read this, this looks a little misleading. I don't want you to think, so let me sort of rephrase this. Why not try using a sample standard deviation? And so maybe if we phrase it like this, turns out that this is the quote unquote correct formula. So maybe I did a poor job explaining this. So I'm sort of giving you a hint here what the correct formula is going to be. But the question and what I'm really trying to get you to think about is why? Why? Now, I'll caution you, if you go to the internet and start Googling the central limit theorem, you're probably going to find things that are overwhelming, because it's typically written in the language of calculus, not the language of the level of math in this course. So you have to be careful. But what's at play here is this big idea of what we call the central limit theorem, and these ideas of things we sort of have intuitive ideas for, called the law of large numbers. So what I really hope is that you take some time to understand what this sort of class was about. It's about stimulating questions on what we're doing. The stuff we did last class is basically toy examples. And now we want to start thinking about how do we make these toy examples more useful for the real world. And that leads us to those questions I wrote at the beginning of class. And the one way we will study them is this thing called the central limit theorem. And in order to understand the central limit theorem, we lead with this example that I started but didn't finish. And of course, we'll finish it next class. But I want to use this as a place for you to try to think more deeply about what we're doing, not just calculating numbers. So I hope you'll do that. I hope you'll read about this stuff. And hopefully I've encouraged you a little bit to want to learn. Now, maybe I did a bad job at it. I don't know. It's possible. It's hard to get a feel for how things go when we're sitting at computers. But anyhow, before we go, does anybody have a question about this? Comments? I'll be sure to answer them if you have them. Yes, no?